These are the notes to begin Unit 7, Exponential and Logarithmic Functions. If you had Algebra 2 last spring, you probably didn't get to this, so I plan on spending more time on this normal, and it's an important part of Algebra 3. So this first section, 4.1, is introducing you to exponential functions. Exponential functions or is any kind of a function with a variable as an exponent. So you see this b here. Well, b is represent a number, and b can be any number. It could be something like this: f of x equals 2 to the x, where b is then the value of 2. Or I could say y is equal to 1/2 to the power of x, but the variable is the exponent. So once again, b is just not equal to 1. I could have g of x equals 10 to the x power. I could have h of x is equal to 323 to the x power. So the bases are all different. It's that the exponent's a variable. So what happens is you have some kind of a value, so we call it the output, but the value is equal to the base and then the exponent. There's actually a lot of information that's going to be coming after. You might feel a little bit like overloaded first, but we'll keep working on it. If an exponential function has a natural base, the base is the value e. So e in your calculator is in two different places. I can find it over here with the division symbol. So it'd be second, and then the division symbol gives me this value for e. And when I hit enter, the value of e is 2.718. It's like pi. You cannot turn that back into a fraction. If I tried to turn it back into a fraction, it's not going to go. It's a value just like pi, where it's irrational, cannot be turned back into a fraction, and it continues. So if I had something like y equals e to the x, that's the natural base. And e is approximately equal to 2.718. Keeps going, and like I said, it is irrational. It cannot be turned back into a ratio. The domain of every exponential function is all real numbers, because what happens is you graph this, exponential functions typically look like this. So as x is going to the left, it's going to just keep going forever. And then as this is going up, x is going to continue to go to the right forever. So it goes to the left forever, and it goes to the right forever. The range of an exponential function is going to be from the asymptote either up or down. So the typical function, exponential function, looks like this, and there's going to be an asymptote right here. So my range would be from the asymptote to infinity. And it doesn't include, so it'd be y greater than whatever the asymptote is. If it's been reflected over the x-axis and it looks like this, it's going to be from negative infinity to the asymptote. Or y less than whatever the asymptote is. It doesn't include the asymptote. It's not going to touch the asymptote. So some different examples. If I had y equals 3 to the x. So what happens with y equals 3 to the x is your x-axis is your y-axis. There is a horizontal asymptote at y equals 0. It's always going to go through this point 0, 1, and it's going to look like this. So this horizontal asymptote occurs for every single exponential function. If we transform this function, it would change the asymptote. So what's going to happen here is this base is a 3, is going to be an exponential growth. So if you did do this in Algebra 2, one of the things that you were supposed to know for the SOL was if something's a growth or a decay. With this function here, the base is 1/2. The function looks like this. It's still going to go through the point 0, 1. It still has this asymptote at y equals 0. And this is considered a decay. So as long as the base is greater than 1, it's a growth. If the base is less than 1, it's a decay. We don't talk about that so much, but in science classes you do. I could have one that looks like this with a negative in front, and we're going to talk about transformations in a minute, but this is going to be an x-axis reflection. So if I took this base of 3 and reflected that over the x-axis, it's going to be down here. And where we get the values are going to show up in a little bit. They're a little bit different. So I still have my horizontal asymptote at y equals 0. And it's just a reflection over the x-axis. Now to talk about translations. We're not going to, I don't touch on growth, or I don't talk about stretches and shrinks with this. It's really just talking about the basics, vertical translations, horizontal translations, and reflections. So a vertical translation is if you had b to the x power plus c, this is going to go up c units. If you have the function equal b to the x minus c, this is going to go down c units. And I'll do a couple examples in a minute. If the c is part of the exponent, so x minus c is going to go right c. X plus c, this is part of the exponent. This is going to go left c. So this is just like before when we did transformations, and transformations are like this for everything. If the constant, the c value, is with the x, it's moving right and left. If it's not with the x, it's going to move up or down. And reflections are the same way. If you change the y, or if you change the x value, so think of it this way. This is what an exponential function looks like. If I take this point here, which is xy, and I change that point to negative xy, it's going to take, instead of being over here, it's going to be over here. So instead of a positive x, it's going to be a negative x. It looks like this. So a negative x is going to be a y-axis reflection. If you change the value of the function itself, the y value, that's going to be an x-axis reflection. Most of you have done very well with that, but we've not done it in a while, so it's worth going back over and explaining it for this. Now we're going to look at the graphs of these. So, like I said, basic exponential function is f of x equals b to the x. Well, b can be any number except for 1, and I can't graph it on a number line or in a coordinate plane because I don't have any numbers to pick points. So I have to choose what I want b to become. So I'm going to let b equal 2. And the reason I use 2 is just the easiest one to graph. So if I took and made a table of values, and the ones I'm going to choose are -2, -1, 0, 1, and 2. And I'm going to put those into the equation. So y equals 2 to the x power. If I put a -2 in for x, 2 to the -2. From Algebra 1, if you remember, a negative exponent makes it 1 over 2 to the positive 2 power, which is equal to 1/4. So I'm going to plot the point -2, 1/4. If x is -1, 2 to the negative first power is 1 over 2 to the first power. So -1, 1/2. Two to the 0 power. Anything to the 0 power is equal to 1. So this is why the y-intercept for all exponential functions, unless you've transformed them, is going to be the point 0, 1. 2 to the first is 2, so I'm going to plot the point 1, 2. 2 to the second is 4. So I'm going to plot the point 2, 4. And we could keep going. 2 to the third power is 8. 2 to the fourth power is 16. But that gets a little bit ridiculous. So we're going to stop here. And that's what the exponential graph looks like. So I've got this horizontal asymptote at y equals 0. My domain is all real numbers. My range, it doesn't go below 0. It never even touches 0. So it starts at 0 with a parentheses and goes up forever to infinity. Or you could say y is greater than 0. And it has a y-intercept. It does not have an x-intercept. Now I'm going to look at transforming each one of these and give you a little bit more information. So if I took y equals 2 and raised it to the x plus 1 power, this is going to go left 1. And I just look at the parent graph. I don't go and plot all the points. Again, I could, but to me it's easier to do transformation. If I'm going to go left 1, I'm going to take this point 0, 1, and I'm going to move it over left 1. And then I could go from there. This point 1, 2 becomes 0, 2. This point 2, 4 becomes 1, 4. And that's really all I need to graph it. Like I said, my domain is all real numbers. My range is still going to be the same range. It's going to be 0 to infinity. But now my y-intercept has changed. My y-intercept is the point 0, 2. But my asymptote did not change. So my asymptote is going to be y equals 0. It doesn't matter if I move left or right, my range won't change. My range will only change if I move up or down. Same thing with my asymptote. This is a horizontal asymptote, so it will only change if I move up or down. Let's try another one. Let's do y equals 2 to the x power and then minus 3. The minus 3 is not with the exponent. So this is going to go down 3. So at start at 0, 1, that's the point I always start with. I'm going to go down 3. So 1, 2, 3. There it is. I'm also going to take my my asymptote and move that down 3. So if it was here at y equals 0, it's now going to be at y equals 3. The point 1, 2 comes down 3 and now becomes 1, negative 1. My point 2, 4 comes down 3 and becomes a point 2, 1. And it looks like this. And when you're graphing these, I do want to see the actual points. So now my range has changed. My range is going to go from negative 3 to infinity. My intercept, I have a y-intercept that has moved down to 0, negative 2. And now I have an x-intercept. To find my x-intercept, I let y equals 0. So if I put a 0 here for y and solve it for x, I'm going to get a decimal. So we're going to leave that go till later on, but it's somewhere between 1 and 2 that it crosses the x-axis. And like I said, my asymptote is y equals negative 3. The next one I'm going to do is y equals 2 to the negative x power. This is going to be my y-axis reflection. So if I think about the point 0, 1, if I reflect it, it's going to stay right there. This 1, 2 is going to come over here to negative 1, 2. 2, 4 comes over to negative 2, 4. So it didn't move up or down or anything, so my horizontal asymptote is still y equals 0. My range is still 0 to infinity. My intercept is still 0, 1. And my asymptote is y equals 0. I like working with exponents and logarithms. I'm not sure why, I just always have. Let's do a few more. Okay, the next one I've chosen would be y equals 2 to the x minus 2 plus 4. So minus 2 means this is going to go right to and this plus 4 means it's going to go up 4. So I would start at this point 0, 1, I go right to, and then up 4. I start with point 1, 2, I go right to, up 4. Then I go to the point 2, 4, I go right to, and up 4. And I'm going to draw my asymptote also. It's going to make this easier to see. If I went up 4, my asymptote is going to move up 4. So when I draw that, I don't want to cross it. So it's going to come down and just slide right along it. So my range goes from 4 to infinity. My intercept moved up 4. So instead of 0, 1, it would be 0, 5, but now it's also moved over. So it's changed a little bit. It's not right at 5. To find my intercept, I would go y equals 2 to the 0 minus 2 plus 4. 2 to the negative 2 is 1/4. 1/4 plus 4 is 4 1/4. So my intercept is going to be the point 0 and then 4 1/4. And my horizontal asymptote is going to be y equals 4. Let's do y equals negative 2 to the x power. Negative 2 to the x power is going to be an x-axis reflection. I'm changing the y value. Think of it, most of you do very well when you talk about quadratics, and you know if you put a negative in front of the x squared, it flips it upside down. Same thing's going to happen here. So instead of the point 0, 1, it's going to be 0, negative 1. Instead of 1, 2, it's going to be 1, negative 2. Instead of 2, 4, it's going to be 2, negative 4. So this is an x-axis reflection. The range now is not 0 to infinity, it's negative infinity to 0. When writing with interval notation, the smallest number gets written first. Negative infinity is definitely smaller than 0. My intercept changed to 0, negative 1. And my horizontal asymptote is y equals 0. One more graph. Let's look at this y equals e to the x. This makes people uncomfortable. So I could go into a calculator and I could figure out what these values are. I'm not going to worry about the negatives. I'm just going to do 0, 1, and 2. E to the 0 is equal to 1. So I'm going to plot the point 0, 1. E to the first, well, I said E was about 2.7. So we're going to say it's about equal to 2.7. And if I have E squared, if I do that in the calculator, it's about 7.4. So at 2, I go to about 7.4. That's enough. I've got 3 points. It looks like that. My horizontal asymptote is the same. So my range is going to be from 0 to infinity. My intercept is going to be the point 0, 1. And my asymptote is going to be y equals 0. I have one more sheet of paper for these notes. The one thing we do in Algebra 3, and if you do math analysis, we'll do it there too, is we talk about applications. Compound interest applications are one that some students are really interested in. It doesn't seem like you're really doing math. It's more finance, and I can come up with problems that make more sense for you. So there's these two formulas. Compound interest, if it's compounded for however many periods in a year, and continuous compounding. Continuous compounding uses the value e. So that's one reason we talked about that. For these formulas, you do not have to have these memorized. If you do them enough, you have them memorized. They're not hard to remember, but you don't have to have them memorized. I'll type them on any quiz or test that you're going to have. A stands for the account balance. It's how much you end up with. So if you deposit money into a savings account, after so many years, it's how much money is in that account. P is the principal. It's how much you begin with. If you want to deposit money into an account, it's how much you deposited. Likewise, if you have a loan, it's how much you borrowed. The interest rate is always going to be a decimal, so it's going to be represented by R. So if you have an interest rate of 4%, you're going to use the value 0.04. Time is going to be the variable t, and time could be days, years, months. It depends on the problem that we're talking about. It will always be defined what unit you're using. For these problems, we're going to talk about time in years. So the only complicated one is the value of n. That's going to be the number of times in a year interest is compounded. So there's some standards. There's a lot of different ones. If something is compounded yearly, once a year, n is equal 1. If something is compounded, money is compounded biannually. Bi means 2, n is going to equal 2 for biannually. Quarterly is 4. Most companies work on finances in a quarterly basis. If you make a lot of money, you usually pay your taxes quarterly, so you don't have to pay as much all at once. N equals 12 would be monthly. There are 12 months in a year, so that's why n would be 12. Weekly, there are 52 weeks in a year. So if something's compounded weekly, you'd use 52 for n. If it's compounded daily, you would use 365 for daily. So let me do a couple examples. Say you decide to invest $5,000. So $5,000 is my A. And an account that pays 4% interest. Well, 4% interest tells me that R equals 0.04. I just realized I made a mistake. This 5,000 is not A, 5,000 is P. It's your principal, it's what you start with. The other thing I have here is it's compounded monthly. If it's compounded monthly, n is going to equal 12. You want to know how much money there will be in the account after 16 years. So 16 is t. And then we're just going to use the formula. So A is going to equal 5,000, 1 plus 0.04 over 12. And then raised to the n, which is 12, times t, which is 16. And then I'm just going to type that in the calculator exactly how I have written. So 5,000, 1 plus 0.04 divided by 12, raise it up, 12 times 16. Do not do this any other way. Put it all in your calculator in one shot. Hit enter, I get 9472.317. Since this is money, I'm going to go 2 decimal places. So if you invest $5,000 and you get 4% interest, it's $9,472 you have after 16 years. 4% interest is actually very high. You're not going to get that. Years and years and years ago, you might have, but the economy has changed so much, you're not going to get 4% interest on money you've deposited. Now, if you get good in finances, and you will be better at it than I am, you might be able to make money if you know the right place to invest your money. Okay, another example. Say I want to borrow money from a lender that compounds interest continuously. So this thing, when it says continuously, that's important. That means I want to use the formula A equals P, E, R, and T. So R and T are the exponent. It's a rate of 9.8%. So I know my rate is equal to 9.8 divided by 100. So 0.098. The loan is for $20,000. So I know my principal is $20,000. That would be if you were going to buy a decent car. 9.8% interest rate is actually a pretty good interest rate if you borrow money. Right now, house loans are in the like 2.3%, depending. And it varies. Your interest rate that you get on loans vary depending on how much you're borrowing, how long you want to borrow, your credit history. So all those things. It says how much money will you pay back if the loan is for 7 years. Right now, it amazes me. You can take a car loan out for 7 years, which is, I think, insane. I would never do it. So I think you're going to be surprised. So if I did A is equal to 20,000, E, and then R is 0.098 times 7. Type it in the calculator. So 20,000. I'm going to get the E. I'm going to hit second, and then this natural log button down here. And what that does is it gives me the E already raised to a power. So then I'm going to type in 0.098 times 7. And I always double check before I hit enter, make sure that I've hit all the right buttons, and I hit enter. So it's 39,715. And 13 cents. So what that means is if you borrow money for $20,000 for 7 years at a 9.8% interest rate, you're going to pay back almost $40,000. This is where I like to explain to people, you don't want to borrow money unless you really have to. You're better off saving your money to get what you want. Unfortunately, the American society, we borrow a lot of money and we end up paying money back. I would rather save my money and not give it away to somebody else. So hopefully you find that interesting.